Hello and welcome back. The board is containing a lot of things right now, but please don't be overwhelmed. We're going to go over everything slowly and carefully so that you get it all. The purpose of this video is to apply the concepts we've been studying, which I've summarized up on the top, to some problems from your textbook. So we've been looking at fluid statics. Fluid statics, of course, deals with pressures. Pressure is force divided by area. This is newtons per meter squared as a unit, which we also call a Pascal. The three different types of pressure here are gauge, atmospheric, and absolute or total. Gauge pressure is the pressure an object experiences if it's submerged in something else besides the atmosphere. So this is the density of whatever that fluid is that it's submerged in times the acceleration due to Earth's gravity times how deeply it's submerged. There's atmospheric pressure, which we're going to use the value of atmospheric pressure at sea level dry air. That's 1.013 times 10 to the 5th pascals. And then there's absolute or total pressure, which is just the sum of gauge pressure and atmospheric pressure. Density gets the symbol rho, and it's mass divided by volume, so in units kilograms per meter cubed. We realize there's a buoyant force felt on an object when it is submerged in a fluid, and that fluid is in a gravitational field. That buoyant force is equal to the density of whatever the fluid is times the acceleration due to Earth's gravity times the volume of the object. And note that this volume is only the submerged part of the object's volume. So if only half the object is submerged, we only use half its volume there. So the buoyant force only has to do with the part of the object that is actually underneath the surface. It has to do with the fact that there's pressure differences between the top of the object that is in contact with the fluid and the bottom of the object that's in contact with the fluid. The bottom of the object's more deeply submerged, so it's going to feel a larger force as a result of the larger pressure being there. So the two problems we're going to be looking at from your textbook, OpenStax, is 1118 and 1125. And I've worked them out here ahead of time, but we're going to read it and then we're going to go over each and every part. So 18 reads, the aqueous humor in a person's eye is exerting a force of 0.300 newtons on the 1.10 centimeter square area of the cornea. A, what pressure is this in millimeters of mercury? And in part B, is this value within the normal range for pressure in the eye? So first of all, the aqueous humor is the liquid that is contained within your eyeball, keeps everything lubed up. And the cornea is the transparent part of the eyeball in the front. So it's not the white. The white is the sclera, but it is confined by that black, the cornea is confined by the black rim inward. So it's the front of the eye, the transparent part. And in this problem statement, we're given the force being exerted on the cornea by the aqueous humor, and we're also given the area of the cornea. So we're asked to find the pressure in millimeters of mercury, and we're asked if this is within normal range. Those are the two questions we want to answer. So first of all, part A, we just want to know the pressure. This is force per unit area. So the force is 0.300 newtons divided by the area of 1.10 centimeters squared. But a centimeter squared is not the standard unit for area. A meter squared is the standard unit. And remember, when we're combining units, we want to keep things in standard units to stay safe. And so we're going to convert the centimeter squared to meter squared. And how are we going to do that? We're going to do it by multiplying by a ratio whose value is 1. So notice that when I multiply by 100 centimeters is the same as 1 meter, I get 1 unit of the centimeters to cancel in the denominator with the centimeters in the numerator, and I'm left with newtons per centimeter per meter. So I need to multiply by that ratio once again so that I can cancel both units of centimeters in the denominator. So when I do that, I get 2.73 times 10 to the 3rd pascals, or newtons per meter squared. Now we want to convert that to millimeters of mercury, so we need to go to the textbook and look at the table of conversions that is in chapter 11 to find the conversion from pascals to millimeters of mercury. And you'll see when you look that up that 1 millimeter of mercury is the same as 133.3 pascals. So I can form a ratio by dividing both sides by either the left side or by the right side. So I take my number 2.73 times 10 to the third pascals, and I want to get rid of pascals and get millimeters of mercury in the numerator. So the way I want to rearrange the ratio then is to have pascals in the denominator and to have the millimeters of mercury in the numerator. And when I do that, the pascals cancels and leaves me with units of millimeters of mercury. So I get 20.3 millimeters of mercury. Then if I look in the table, look within chapter 11 at the normal range for the forces experienced on the cornea by the aqueous humor, I find that the normal range is 12 to 24 millimeters of mercury, and we see that we're well within that range, at the higher end of it, but still well within the normal range. So that is 1118. 1125 asks us about a hydraulic system. And we haven't talked about hydraulics before. It's a pretty simple concept, though. Here is a hydraulic system. Hydraulic system has two pistons. Normally, one is called the slave piston and one is called the master piston. And there is a confined fluid that contains these two pistons. So inside this dashed line here is a confined fluid. The principle of hydraulics states that any pressure change felt within a confined fluid is felt undiminished throughout the fluid. So if I change the pressure at this point, that pressure change is felt throughout the entire fluid, completely undiminished. That is the principle of hydraulics, and that's going to be the principle that we're applying to this problem. So now let's read the problem statement. What force must be exerted on the master cylinder of a hydraulic lift to support the weight of a 2,000 kilogram car resting on the slave cylinder? The master cylinder has a 2.00 centimeter diameter and the slave has a 24.0 centimeter diameter. So I've written the information over here. We know the mass of that's going to be placed on the slave cylinder, and the weight or the force then felt on the slave cylinder due to the fact that we place this mass there is just going to be its weight. So it's going to be the mass of on the slave cylinder times the acceleration due to Earth's gravity. So there's that product right there. We're asked to find the force that we need to exert on the master cylinder to support, to keep this in equilibrium, to keep the slave cylinder's 2,000 kilogram car in static equilibrium. We're given the diameter of the master cylinder is 2.00 centimeters and the diameter of the slave cylinder 24.00 centimeters. So we're going to apply the principle of hydraulics, and when we exert a force on the master cylinder, it then translates to a pressure change being felt on the fluid right underneath the master cylinder. So I exert a force over this area. The force divided by the area of the master cylinder is going to translate to the pressure being felt here, and that pressure change is going to be felt undiminished throughout the fluid, and specifically right here underneath the slave cylinder. So I can say then that the pressure felt at the slave cylinder is going to be equal to the pressure being exerted on the master cylinder. The pressure that the slave cylinder is going to feel needs to support this car, which is the 2,000 kilogram car, and its weight then is the 2,000 kilograms times the acceleration due to Earth's gravity distributed over the area of the slave cylinder. And the force exerted on the master cylinder divided by the area of the master cylinder is going to translate to that pressure. So setting these two pressures equal to each other, setting these two ratios equal to each other, and solving for the force we need to exert on the master cylinder gives us this solution right here. And these are circles. These areas are circles, so I can write this then as the master's the slave's mass times the acceleration due to Earth's gravity times pi diameter of the master cylinder squared over 4. Remember, this is the pi r squared is the area of a circle. So the radius then is half the diameter, but I need to square it. So that is the ratio I get. And then for the slave's area, same thing, pi times the diameter of the slave squared over 4. The 4's are going to cancel, the pi's are going to cancel, and we're just going to be left with the mass of the slave cylinder times the acceleration due to Earth's gravity times the ratio of the master's diameter squared to the slave's diameter squared. Since these are, this is a ratio of diameters, I don't need to worry about taking these centimeters and putting them in units of meters because they're going to cancel. So I'm fine leaving it just like this and leaving these units just as they are, and I have all of the numbers defined over here. And so when I plug in all of those numbers, what do I come up with? I come up with a force that we need to exert to support this car of 136 newtons. So if we push down on this master cylinder with a force of 136 newtons, we're going to be able to support or exert an upward force on the slave cylinder that's going to balance the downward force on the car and keep it in equilibrium. And notice here that the force of gravity being exerted on the car is the 2,000 times the 9.8, and that's going to give us a force of 19,600 newtons. So the force being exerted on the slave cylinder is 19,600 newtons. We're able to magnify our 136 newtons to a force of 19,600 newtons using the principle of hydraulics. And it has to do with the fact that we make the area of the slave much larger than we make the area of the master. So, and 2 applications of applying fluid statics, and we'll work a couple more problems in the next video just to get a little bit more of these nuances ironed out. So we'll see you next time.